This lecture is about the chapter 22 for our textbook, and so that is inspection technologies. And so I wanted to go ahead and walk through this with you. And so when looking at chapter 22, it's really important that you look at the YouTube videos I posted, and I'll make reference to them again. But those videos are going to give you good visuals for some of the technology. This lecture is really short, a lot shorter than the textbook content, because the textbook content gives you kind of 2D diagrams and labels different parts of the equipment, and this is giving broad strokes with the expectation that you'll go watch those YouTube videos that actually show you the physical devices and how they work. So when we think about inspection metrology, we're looking at the science of measurement. And there's two types of measurement that we would really focus on in production. And the first would be manual measurement. That's not really covered so much here because our focus is on technologies. And so calipers, micrometers, snap gauges, go, no-go gauges, those all are manual measurement devices that we're able to take readings with and record those readings to verify that something is within the desired specifications. The other way is using automated technology, which is the focus of this lecture. But whether it is automated or manual, when we're looking at measurement, usually you're measuring a quantity with a device that is looking at length, mass, current, temperature, luminosity, time, or other quantities. So in manufacturing operations, a lot of times your go, no-go gauges or snap gauges allow you to inspect a certain dimension, like a length, a width, a height, and it's a set height and it either passes or it doesn't. If you're looking at production of things that are measured by volume or weight, they might go across an automated scale and weigh each individual component. We talked about that a little bit before COVID outbreak, and we were in class talking about packaging technologies and how that inspection works. Temperatures are measured for various processes, and then other quantities as well. So you can see that the measurement is going to look different and use different equipment depending on what quantity is being measured. And so our focus is primarily from a manufacturing standpoint, which means a lot of times we're looking at physical dimensions, even surface roughness or smoothness or parallelism, or inspecting manufacturing processes like a weld to make sure that the weld is complete and will hold sufficiently. So when we look at the instruments themselves, precision and accuracy become really important. And so accuracy is how close the measured value is to the true value. Excuse me. So if you have a snap gauge, you're able to see it either is or is not correct. With your calipers or micrometers, you might be looking at how closely something is, and you might have a tolerance, a range that tells you within this given range, you are able to accept the product because it meets manufacturing specifications within the given tolerance. But the accuracy of the measuring instrument should always be as close to perfect as possible. And the way that we do that is we use established guides, and that's a process called calibration. And so we can calibrate it by a device by taking a known standard and then comparing that to what the device actually measures. So if you have a set of calipers and you have a known 1-inch standard, you can then verify that the calipers do in fact reflect 1 inch. Or if you have a scale and you have a standard weight of 10 kilograms, you can verify that the scale does in fact measure it to be 10 kilograms. So that's accuracy. Precision is about repeatability. How often can you get the same measurement in a row? And when you're looking at that precision, the rule of 10 says that the measuring instrument must be 10 times more precise than the specified tolerance. So a lot of times in machining, you would think about a machinist rule and say, okay, if we have a measurement that the tolerance is plus or minus 0.01, or we're looking at the hundredths column, then the device itself should be able to measure to the thousandths. And so that factor of 10 is always added as the level of precision required for the device. The resolution directly relates to that because the resolution is the smallest variable that can be detected. So if the resolution of the device is to the thousandth, that means that the marks on the device or the capabilities of the device are to the thousandths. If you think of a basic steel rule that's in inches, you might get down to an eighth of an inch or a 16th of an inch. That's the resolution of the device itself. How long the instrument takes to measure might be something with a scale. If you have it on an automated packaging line, you would want that measurement to be taken very quickly so that you are able to keep the line speed going at the rate of production without missing a measurement. Another factor would be like temperature. So in pharmaceutical manufacturing, for our pediatric formulas, they were all liquids. And so we had to measure different temperatures, and we used digital thermometers that gave us temperatures in Fahrenheit and Celsius ratings to the hundredths place, and it was pretty much instantaneous. And so for production capabilities, you want measurements to be done pretty much instantaneously. If you are doing measurements offline by hand, the speed of the measurement is usually the speed of the operator. So then reliability, cost of the device all become factors as well. So when you look at accuracy versus precision, from a quality standpoint, you're always going to want high precision. You want repeatability. You want to see the same thing over and over, because even if it's inaccurate, if it's very precise, I can just make a small adjustment to move that reading. So maybe I'm getting readings that are supposed to be at 9.5, and I'm getting them over and over, 10, 10, 10, 10. Well, I can adjust that setting down 0.5, and then I would be getting 9.5, 9.5, 9.5. But if my readings are 8, 7.3, 10.2, 6.8, that's a lot more variability. That's hard for me to create precision with all of that variability. So what we want from our process is we want both accuracy and precision. So for analog instruments, we're able to have a continuous variable. We're able to move that easily, and it has an infinite number of possible values. For digital measurement, it's always going to be a discrete number that's set in advance. So maybe it's to the tenths, maybe it's the thousandths, maybe it's the 10,000ths, but those incremental values have already been established. What's very helpful, though, is that you can read it clearly. So again, think of your digital thermometer, whatever the level of precision the device has. For most of us at home, it's just to the tenths place, 98.2, 99.3. But it's very clear to read on the output screen of the instrument. Also, digital measurements can be automatically recorded on a computer, which is very helpful in gathering data for ongoing quality measurements. When we think about non-contact inspections, we're looking at sensors and probes that can measure the object without touching it. And those non-contact inspections can be optical or non-optical. One of the reasons we would want that is usually it's faster, it's automated. The production can continue, like you can do that on a production line. And when you look at vision systems, it's going to show you a couple different optical sensors that are measuring height, width, presence or absence of a certain component, a fill rate of a certain item. All of those things can be done, and you can have an 100% inspection at the rate of production without ever taking anything offline. And then the only product that's segregated is product that's found to have a defect. Non-optical is a device that is a non-contact device, but that is not using light. And so when we look at the CMM machine, the coordinate measure machine, that's an actual probe that will be able to measure all of the dimensions of an object and compare them with a part drawing. So instead of having an individual measure the part for each of those dimensions and compare them to a drawing, you can upload a CAD drawing into the computer, and then the coordinate measuring machine will compare the physical part to the computer drawing. And so you have a much higher level of accuracy and precision, as well as being able to complete all dimensions of the part very, very easily. And all the person has to do is load the machine, unload the machine, and verify that the drawings were correct. So when you look at using CMM machines, again, it reduces the cycle time, so you're able to inspect more things faster. The CMMs are able to measure any device. You just put in any CAD drawing, and so you don't need specific tooling where you might have like a depth gauge is different than a standard caliper. You would not need those different types of manual devices because you're able to measure all the dimensions using the CMM. The operator error is reduced. And again, each of those measurements are done based on individual drawings. And so you can switch parts from one to the other very quickly without having to change a setup or change the tooling. So it's much faster. For machine vision, we're looking at acquiring images, and that computer vision system can be done both for 2D and 3D applications. And again, using those cameras, light, laser, comparing to what the desired quantity would be, you're able to use vision systems to inspect 100% inline inspection. And again, this could be presence or absence of a label. This could count the quantity of a given item. It could inspect for different levels, fill rates, location of variables. And again, the YouTube video, both for the CMM and for the machine vision, will give you a lot more detail on the components of those devices, how they work, what sort of applications that they're used for, and what are the different components to make those work. And so again, just consider that required viewing as if it was part of the lecture. So we can use a vision application for, as I said, the inspection. And these again are some of those items, whether it's presence or absence of something, location or number, flaws in labels, for sorting or counting, and then also visual controls. Then other optical inspection methods would include things like an optical comparator, which would be analyzing a part compared to a known standard, a microscope that just allows you to look at specific very fine detailed tasks. So for example, you might use that for some of the welds to ensure the welds are correct. Laser systems, linear arrays, or optical triangulation, which can be used for location of items. Non-contact, non-optical inspection techniques are those that, again, do not require touching the item in any way, but they're not using light-based technologies. So electrical field techniques, you might be measuring capacitance, inductance, resistance. So those measurements can be done. So for example, if you have a multimeter, those measurements can be done. X-ray techniques can be done. Again, that also might be used for welding. Is some welds are X-rayed depending on the criticality and where they're located. And then ultrasonic inspection is using sound waves. That can be used for thickness or also position and orientation. So those are the different types of inspection covered in chapter 22. As I said, the length of the chapter is actually much longer because the length of the chapter itself is looking at detailed components and operations. Also, some of those comparative measurements. And on Thursday, we will be actually doing some of those measurements as part of the recitation. Some of those questions were posted up for homework from your textbook, and that Word document is posted. I will be doing those other questions on Thursday. as always, I hope you stay safe, stay healthy, stay inside, and let me know if there's anything I can do to help.